Hey there, we're in the last PowerPoint lecture over chapter 14, and depending on the amount of time this section takes, I might also get into chapter 15. So this last section discusses the motor output or the response to the information that was sent to the CNS. There are typically two major responses that our somatic motor division can have. The voluntary response is a response where we consciously are aware of something and we choose to respond to whatever is going on. Involuntarily, this is something that we wouldn't be conscious of. And so we really don't have the ability to choose. We just do it. Examples that I put on there, swatting a fly off our arm or scratching an itch would be another example. Involuntary would be breathing. That would be an example of an involuntary response. Sneezing, involuntary response. So when we think about motor responses, we always, and the frontal lobe, we always bring up the accident that occurred to a railroad worker known as Phineas Gage. So Phineas Gage was a worker on the railroad, a very pleasant individual in general, and during his time working, I don't know how it happened, but some accident occurred and one of the railroad ties embedded itself into his frontal lobe, or through his frontal lobe. So it went right through his face, through his skull, of course, and out, and it damaged that frontal lobe. The frontal lobe is where we have decision and goal making. This is where we get our focus, our personality. This is where our motor movements and fine-tuning those movements occurs. So when this happened, it changed his personality greatly, and that's one of the reasons we know that personality and focus occurs here, because his personality had changed so dramatically. We also know that in the 1800s, they didn't have all the pain medicines that they do today, and so the main thing that they used for pain actually was alcohol, and so he did become an alcoholic for a time to treat the pain. So his personality changed partially due to the railroad tie damaging his frontal lobe, but also because of the alcohol he was drinking. Eventually, though, he was able to overcome this accident, and he became a very prominent stagecoach driver. So became a good person. He wasn't angry anymore. So what this shows is that your brain can eventually, I won't say heal itself, it's not like he got new neurons growing, but that it can fix itself to the point where other regions can take over. And we already knew this, or if you didn't know this, now you do know this, that when one region of the brain starts to, or it becomes damaged, another region can sometimes take over when it's in that cerebral cortex. In the frontal lobe, then, we have a prefrontal cortex and a primary motor cortex that we look at for motor response. The prefrontal cortices includes a premotor cortex and a supplemental motor cortex. These are located lateral to the actual primary motor cortex, and these areas function in assisting the primary motor cortex in production of movement, so planning and coordinating those movements properly. The premotor cortex functions in stimulating core muscles to allow proper posture, whereas supplemental motor area is thought to be used in helping with planning and coordinating movements of the body. Broca's speech area is anterior, the premotor cortex, and it functions in stimulating the muscles associated with speech to move properly for speech or for sound. And the frontal eye fields stimulate our eyes to move towards different stimuli for vision. So now we have, and I think I skipped a slide, sorry. So I'm going to go to this slide. This says the same thing really, so I'm just going to go to this one, okay? Now let's look at our actual motor response. So within the cortex, the cerebral cortex, we have motor neurons that are called Betz cells that synapse with other motor neurons within the brainstem. And they form two different tracts. They form a corticobulbar tract, which is considered an ipsilateral tract. This means that the information moves from the cerebral cortex to the brainstem, and the information stays on the same side of the brain. Whereas the corticospinal tract moves from the cerebral cortex to the spinal cord, it's considered contralateral. So the information that is processed on one side of the cerebrum actually moves to the opposite side of the body for the response. This is just the information about this figure. So this is the corticospinal tract that you're looking at here. Both appendicular and axial control to the body occur through that corticospinal tract. The lateral corticospinal tract controls appendicular movements, whereas anterior corticospinal tract controls the axial muscles. And the motor output occurs through the ventral horns. So remember, the dorsal horns took in sensory information. Ventral horns send skeletal or muscle information out, or motor information out. So let's talk about what, so you know, skeletal muscle movement is something that we are consciously aware of and that we can choose typically. But a reflex is a pre-programmed response to some stimulus that is unconscious, and we have no control. Well, if it's unconscious, we have no control over. So this is pre-programmed, rapid. It's a response to some stimulus, and there's no response, or there's no control over a reflex. You can't stop a reflex from occurring. Skeletal reflexes would be things like the withdrawal reflex, which you saw in chapter, I believe it was 13. Or no, it might have been the beginning of this chapter. When you were touching something hot and you had to move your hand away from that hot item. That's the withdrawal reflex. That same reflex would be if you're stepping on a nail. You would withdraw your foot very fast. A stretch reflex, think of when the doctor hits your patellar ligament directly below the patella and your leg kicks out. That's that stretch reflex. Corneal reflex, when the very, very bright stimulus comes into the eye, it causes you to start blinking, or if anything irritates the eye, you start blinking. That's a corneal reflex. These are all pre-programmed, that was weird. These are all pre-programmed responses to protect the body. So this is the end of this chapter, but I only have a few slides in chapter 15 that I'm going to go over. So I'm going to jump right into chapter 15, okay? Oh, that looks bad. Chapter 15 is the autonomic nervous system, though you can't really read it here because it looks kind of funny. So I'll turn it to this slide. So autonomic nervous system is associated with the viscera of the body, it's also known as the visceral nervous system. It's the system that allows us to maintain basic homeostatic functions and keeps us alive when something is potentially causing us danger. So when you think of fight or flight, most people think of, a predator attacking prey. We don't really have a lot of predators today that attack humans, but we do have things that set us into this fight or flight response. Think of flight or fight. Yeah, fight or flight, flight or fight. I guess it's the same thing. When you think of a fight or flight response, think of when you are getting ready to take an exam or a quiz in this class or in any class. When you are going on a first date with someone you don't know very well, that excitement and nervousness, that's that same fight or flight response. And of course, if something was chasing you down the street and you were trying to get away, that would be that fight or flight response. So fight or flight is an adaptation to keep us alive in the face of very serious or sometimes not so serious potential dangers. So I'm going to bring this back up. I've shown you this before when we were going through the organization of the nervous system, but I've added in sympathetic and parasympathetic. So here we have, under the autonomic motor division, we have a sympathetic division and a parasympathetic division. Sympathetic here is your fight or flight division. Parasympathetic is your rest and relaxation division. This is where major homeostatic activities occur. When the autonomic division releases neurotransmitters, those neurotransmitters are not just released at the end bulbs. In autonomic nerves, we have within the nerves themselves, we have these varicosities. These are bulges of the postganglionic nerve, and they have those same vesicles that can release chemicals all along the neuron, and this actually allows us to release chemicals much more rapidly so that we can respond more effectively to potential dangers. So, and this is showing this is a figure from your textbook showing connections of the sympathetic division of the autonomic nervous system. It's hard to read on here, but if you look in the book, you can see things that are going to be stimulated by the autonomic nervous system in the sympathetic region that will either cause stimulation or inactivate the different activities. So for the sympathetic division, your eye, the iris, is going to open up, or it's going to get larger, cause it's going to contract, causing the pupil, good Lord, I couldn't think of the word, the pupil to get larger, to take in more light so that we can take in a better picture of what's going on. Lacrimal glands are not that important. We're going to inhibit lacrimal glands unless we need to have them working. I'm looking at some of these. Okay, the heart is going to be stimulated to beat faster, work harder to make sure that we have enough oxygen and nutrients to those organs that we need. And I'm not seeing muscle here. Parotid gland, I don't see actual, just the stomach is going to be inhibited. I'm looking at these, trying to find some of them that are really important. Intestines inhibited, bladder inhibited. The major organs that are going to be excited, the bronchi, the lungs, the respiratory system in general, the skeletal system, the cardiovascular system. Those are all organ systems, the nervous system. Those are all the systems that we're going to stimulate to keep us alive. Whereas here's the autonomic parasympathetic division. These are going to inhibit those same organs that were being stimulated, and they're going to activate other organs. So the eye, the iris is going to relax, allowing the pupil to get smaller. Heart is going to relax so we can slow down the beating. The lungs, the bronchi are going to relax. Those muscles are going to not constrict, but they're going to relax so that we don't have as much airflow going in. We don't need as much airflow. But the small intestines, the bladder, the stomach, these are going to become activated so that we can go about normal physiological activities to maintain homeostasis. And again, we talked about a reflex in a nutshell, which is a pre-programmed response to a stimulus. A somatic reflex stimulates skeletal muscle, whereas a visceral reflex is going to stimulate smooth or cardiac muscle, or sometimes glandular tissue, depending. Somatic reflex, we are conscious of the reflex occurring, whereas that doesn't mean that we get to control it. It's skeletal muscle, but it's still a reflex. Whereas visceral, we are unconscious. So the major difference is the types of activities that are occurring. In a visceral reflex, an example, the startle reflex, which causes your heart to race faster. Sweating is a reflex associated with the increase in body temperature. Oh, sorry, there you go. So both are going to send signals to the central nervous system. And in both cases, we don't tend to recognize what's going to happen, or we don't tend to know what's going to happen unless the stimulus is very strong. That's all I'm really going to talk about in this chapter. So there's more information. The chapter's not super long, but you can definitely read the information on your own. This is all I'm going to go over for chapter 15 though. So I will post this lecture and I will see you guys in class. Bye.